Hello, my name is Oyindolapo, and I'm here to present the steps I took and my findings and observations while fine-tuning, developing a conversational medical question and answer chatbot for the Kaggle Fellowship Cohort 2024. So I'm a PhD student at Western University and also a software development lead of Thompson Realtors. The goal of this whole project is to fine-tune a medical question and answer data set in a conversational style. And the research question is to look at if medical concepts can be simplified enough and accurate for people that are not in the healthcare field or healthcare professionals. For this project, the MedCord dataset was used, and the dataset was developed by Ben Abacha and Dina Dema. And also special thanks to Kaggle and Google platform for allowing this project to be actualized. The overall architecture of the project is we're using GitHub to host the data set, and all the coding was done within the Kaggle space and the Google platform. First, prompt engineering was done to modify the prompt, and fine-tuning was done on Kaggle platform, evaluation of the models. Once we're satisfied with the models are deployed to Hugging Face. We have deployment to Hugging Face. We also have the deployment to Kaggle models. And from there, and also the storage of the model in Google Cloud, Google buckets, connection of the Google bucket, deploying the model to Vertex AI, and connecting with Dialogflow. That is the high-level architecture of the project. So the first thing that was done after prompting, cleaning up our data set is to fine-tune using the Keras library and LoRa. The LoRa was used to efficiently fine-tune the model with fewer trainable parameters. There are some resources constraints, which is the time the resources available to train the data is a constraint for the project. So one of the way of not optimizing the resources, having a balance between the resources that I have and my data set and my training, is to introduce LoRa. Also, to avoid overfitting, Adam W Optimizer was used. After the fine-tuning, this model was deployed to Kaggle models. After fine-tuning and evaluating the model to see that the output is good, it was deployed to Kaggle model. Also, it was also converted to Hugging Face transformer and deployed to Hugging Face platform. The converted Hugging Face model was then pushed to Google buckets, and from the Google bucket, it was deployed to Vertex AI. This was possible, deployment to Vertex AI on Google Cloud was possible through the use of Docker URL. So Hugging Face has some Docker images that are available that you just need to point you use as your base model for deployment. After going through the steps and evaluating, although after the training of the model, there was an evaluation done. After deploying the model, again, another phase of evaluation was done. And it was discovered that while using the prediction Docker image for deployment, the model started as hallucinating. So the deployed model we have on Vertex AI, which used the prediction Docker image, started hallucinating. So we started getting wrong information from it. Comparing the deployed model to the model that was deployed directly, the undeployed model, and the model that was in the buckets, Google bucket, the undeployed model performed better than the deployed model. So this brought about a reason to say maybe something is wrong with how I deployed to Vertex AI or the Docker image. So I went forward to create my own Docker, and the result was okay. The next stage was to use supervised fine-tuning trainer, which is an adapter. So due to the expensive computation resources experienced in the initial training, that is using Keras LoRa, there was need for quantization and adapters. So the SFT trainer offered significant reduction in computation cost and training time. And also the inference generation was faster too. So comparing the inference generation using the Keras and LoRa compared to when using the SFT trainer, there was a faster inference time with the FST. So 6,000 records were used in this instance to avoid hallucination, bias, and overfitting, while for the Keras, the 2,000 records were used. So like I said, we had computation constraints. So the arguments or some the training arguments that was used for the training, we had the evaluation strategy, which was epoch, which means that the model was evaluated at every epoch to help us know the optimized number of trainings to do. So also identify when the model started overfitting. So the batch size was adjusted. So based on our GPU memory, we add 10 max steps, and the optimization was the Adam W, the Page Adam 8, which is a memory efficient version of the Adam W optimizer used in the first training state. So comparing the two approaches that was used for fine-tuning, the adapter was faster in training, more memory efficient, and I could train more data as compared to using just Keras and LoRa alone. And also, using the adapters, it came in a ready-made form to be able to deploy to Hugging Face. Whereas using Keras library and LoRa, I had to convert. There's a script available from Keras to use to convert to an Hugging Face model to be able to deploy to Hugging Face platform. So some of the challenges I faced, apart from identifying which approach to use, were determining what hyperparameters to use. And this was the case of using the adapters. Balancing between performance and computational cost. That was another challenge. While the Keras and the Keras and LoRa training, the initial method performed a little bit better than using the adapters. Using the adapters was cheaper in terms of computational cost, time, and it allowed me to train more data sets using the same resources. So balancing between those two was something I needed to factor in. Also, GPT cost. Thank you to KaggleX program. for giving us credits for the GPC. But in training this, after using the Kaggle, the cost also mattered. So these are the links to all the projects, all the notebooks, and the deployment. Also, I have how I created my Docker, and all that is here. Thank you.